Welcome to Neural Intel. We're jumping straight into a really interesting technical challenge today, figuring out the best way to fill in the blanks when you've got incomplete data sets.
Exactly. We're going to unpack a method called adaptively weighted nearest neighbors, or AWNN.
Hmm.
It's specifically designed for, well, matrix completion.
Hmm.
Estimating those missing entries in a pretty structured way.
And like always, here on Neural Intel, we'll be focusing squarely on the technical nuts and bolts, the implications of the tech itself.
Mm-hmm. Ethical angles, inclusivity, those are important discussions, but not for this deep dive. We're sticking to the algorithms and the math.
Okay, let's dive in then. The paper we're looking at is Adaptively Weighted Nearest Neighbors for Matrix Completion. You can grab it on our Ceph.
Right.
Now, if you've dealt with machine learning at all, you know that handling missing data is, well, it's fundamental. It comes up everywhere.
Oh, absolutely. Think about recommendation engines. They're trying to guess what movie you might like, even if you haven't rated tons of movies before.
Or like in economics, maybe, trying to figure out causal effects when, say, some economic indicators just aren't available for certain regions or times.
Precisely. Incomplete data is almost, the default state in so many real-world scenarios. So getting good methods to fill in those gaps accurately is just crucial.
For sure. And one approach that's been around for ages is using nearest neighbors. The basic idea is super intuitive, right?
Totally. If you're missing a value for one data point, you just look at other data points that are, well, similar to it and use their values to make an educated guess.
You find the neighbors and use what you know about them to infer what you don't know about your target point.
Exactly. And it's funny, the paper actually mentions the concept goes way, way back. Like Al Hazen in the 11th century working on optics, using similarity for inference.
Wow. Okay, that is deep roots. Shows how fundamental the concept really is.
It does. And the paper makes a good point. Even with all the fancy deep learning models we have today, nearest neighbor methods are still really valuable.
Why is that?
Well, mainly because they're often less computationally heavy and they don't force you to make strong assumptions about like the exact mathematical shape of your data beforehand. They're flexible.
Okay. So matrix completion is using this neighbor idea to fill in missing cells in a data matrix, a table of data, basically.
You got it. Taking a matrix with holes and trying to reconstruct the full picture.
Yeah.
And generally you see two main flavors. K nearest neighbors, K and N, where you pick a fixed number, K, of neighbors.
Right, like the 5 closest neighbors.
Or there's kernel regression, sometimes called Nader-Watson. That uses more of a smooth weighting function or a bandwidth to decide who counts as a neighbor and how much they influence the prediction.
So these methods exist. What's the problem? What are the challenges AWNN is trying to fix?
That's the crux of it. The big headache has always been figuring out two things. First, how many neighbors? What's the right K or the right bandwidth?
Okay.
And second, how much importance or weight do you give each neighbor? Do they all count equally? Do closer ones count more? How much more?
And how do people usually figure that out?
Often it's trial and error, like cross-validation. You keep splitting your data, trying different K values or bandwidths, seeing what works best on the held-out data.
Which sounds tedious and maybe computationally expensive.
It can be, yeah.
Yeah.
It's not very elegant, feels a bit like guesswork sometimes. And even if you just decide, okay, all neighbors get equal weight, just finding the optimal number of neighbors, the K, without cross-validation has been surprisingly hard.
Right. And kernel methods have their own issues with picking the bandwidth and the exact weighting scheme.
Exactly. It often lacks a really solid theoretical underpinning for choosing those specific parameters.
Okay, so AWN is stepping in to offer a more, let's say, principled and automatic way to handle this.
That's the goal, yeah. Adaptively weighted nearest neighbors, the name kind of gives it away. It wants to automatically figure out those weights based on the data itself. It tries to tackle the classic bias-variance trade-off.
The trade-off. Too simple a model, high bias, misses the pattern. Too complex, low bias but high variance, overfits the noise.
Precisely. Finding that sweet spot is key. AWNN aims to do that automatically by choosing the weights in a data-driven way.
Sounds good. So how does it work? What are the mechanics? Let's start simple. Maybe imagine we have all the data, just noisy.
Okay, good starting point, the denoising case. When all data is observed, AWN basically does two main things. First, it estimates the overall noise level, the variance, let's call it sigma squared.
Okay. Figures out how noisy the data is.
Second, it calculates these weighted nearest neighbor estimates. And the key is the weight given to any neighbor row is inversely related to the estimated distance between that neighbor row and the row you're trying to denoise.
Inverse distance, so closer rows get higher weights, farther rows get lower weights. Makes sense.
Exactly. Which contrasts with, say, standard unweighted KNN, where your K-chosen neighbors all get the same 1K weight, regardless of whether one is much closer than another within that group.
Right. AWN is more nuanced within the neighborhood. You mentioned the noise level estimate playing a role.
Yeah. The intuition is interesting. Imagine zero noise, perfect data, then the best estimate for an observed value is just the value itself, right?
Sure.
This suggests the weight should somehow depend on that noise level. If noise is low, you'd want to rely heavily on very, very close neighbors, maybe even the point itself if allowed. If noise is high, maybe you average over a slightly wider set to smooth things out.
Okay, that makes sense. So this distance, how is it defined? It's not just the raw difference in values.
Well, the paper talks about a true underlying distance, let's call it rho. This reflects the difference in the underlying signal between two rows, but it also accounts for the noise variance. We can't observe rho directly, of course.
Because of the noise.
Right. So AWN uses estimates of these distances, rho hat, calculated from the noisy data we do have. It assumes the noise is technically sub-Gaussian, which is a fairly standard statistical assumption.
Got it. So it estimates the noise, estimates these true distances, and then uses those to calculate the weights.
Precisely. And this is where proposition 1 comes in. It gives a mathematical upper bound on the expected error for a given row, the mean squared error, or MSE. And this bound depends directly on the weights you choose and those estimated distances, rho hat.
So the goal is to pick the weights that make that error bound as small as possible.
Exactly. Minimize the bound. AWN doesn't just guess weights. It finds the weights that are, in a sense, theoretically optimal according to this bound.
How does it find them?
It turns out you can formulate this weight-finding problem as a convex optimization problem. Equation 4 in the paper lays it out.
Convex optimization. That means there's a single best solution, right? No getting stuck in suboptimal valleys.
That's the beauty of it. You're guaranteed to find the globally best set of weights according to that MSE bound, given your estimated noise and distances.
What about that zero noise case you mentioned? Does AWN handle that correctly?
It does. If you set the noise variance sigma squared to 0 in the math, AWNN correctly determines that the best neighbor is the row itself, giving it a weight of 1 and everything else 0. Perfect data in, perfect data out.
Nice sanity check. The paper also touches on low-rank factor models in the noiseless case.
Yeah, briefly. Even if you don't allow a row to be its own neighbor, if the true noiseless data has some underlying low-dimensional structure, like a factor model, AWNN still does the right thing. It effectively finds the row that's closest in the underlying latent factor space.
Cool. Okay, so we have the core concepts. How does the actual algorithm flow? What are the steps?
Okay, algorithm 1 describes the overall AWN procedure. It's iterative. You start with an initial guess for the noise variance.
Okay.
Then you compute all the estimated pairwise distances, the rho hats. Then comes algorithm 2, the row imputer. For each entry you want to estimate, it calculates a weighted average using the current noise estimate, the distances, and the observed entries in that specific column.
Ah, so it uses the neighbor's values, but only where they're actually observed.
Exactly. And there's also algorithm 3, the weight adjuster, which is a technical step just to make sure the weights used for each estimate properly sum to 1.
And then this whole process repeats.
Yes, you use the imputed values to refine your estimate of the noise variance, and then you repeat the distance calculation and imputation. You keep iterating until the noise variance estimate stabilizes it. It doesn't change much between iterations.
Seems a bit more involved than just picking once.
It is, but the payoff is that it's automatic. No manual tuning of K or bandwidth. The algorithm adapts based on the data it sees.
So focusing back on that denoising case, no missing data for a moment, the theory gets interesting there, right?
Yeah, in the denoising setting, the algorithm basically solves that convex optimization for the weights. Proposition 2 provides a really neat insight. It shows the optimal weights AWNN finds do two things. They effectively select the neighborhood of rows around the target row. Only rows within this neighborhood get non-zero weights, and within that neighborhood, closer rows get higher weights.
So the size of the neighborhood isn't fixed like K, it's also determined adaptively.
Precisely. Both the neighborhood and the weights within it are adaptive.
Ugh.
Then theorem 1 gives you the error bound for this denoising process. It breaks the row-wise MSE down into bias and variance terms.
Standard stuff for analyzing estimators. How does this ANN error bound compare to, say, unweighted KNN?
Well, the paper argues, and Lemma 1 formally states, that the MSE achieved by ANN is guaranteed to be less than or equal to the MSE you'd get from the best possible optimally tuned unweighted KNN method for that row.
Wow, okay. So theoretically, it should always do at least as well as the best fixed K method, and potentially better because the weights are adaptive.
That's the claim. It really highlights the potential benefit of letting the data dictate the weights.
Makes sense. The paper then looks at performance under specific structural assumptions, something about low-dimensional structure.
Yes, to get more concrete results about how fast the error decreases as you get more data, they introduce Assumption 3, a nonlinear factor model. Basically, the true matrix signal comes from a few latent factors passed through a smoothish function.
Okay, assumes some underlying simplicity.
And Assumption 4 says how those latent factors are distributed. Under these conditions, Corollary 1 gives the convergence rate.
Convergence rate, how fast the error shrinks with more data.
Exactly. And the cool result is that AWNN achieves the same optimal convergence rate as unweighted KNN in a specific regime without needing you to figure out the best K. It adapts automatically to achieve that optimal rate.
Very nice. Okay, so it's great for denoising. But the main goal was matrix completion handling missing data. How does it adapt?
Right, this is where things get a bit trickier. If you have missing entries, you can't just find neighbor rows and average their values for a specific column, because those neighbor rows might also be missing the value in that same column.
Ah, yeah, your best overall neighbor might not have the specific piece of info you need right now.
Exactly. So AWNN gets clever. Instead of one set of weights per row, it calculates weights that are specific to each column you're trying to impute a value in. For column J, it looks only at the rows that actually have an observed value in column J. They call this the active set for column J, AJ.
So the neighborhood and weights change depending on which specific missing cell you're filling.
Precisely. The optimization problem for the weights, equation 7, is modified to only consider rows in that active set AJ. Proposition 2 gets adapted to, equation 8. The relevant neighborhood, RAJ, is now built just from those active rows.
And lemma 2 says something about the distances within this active set neighborhood.
Yeah, lemma 2 essentially provides some guarantees that even when restricted to this active set, the neighbors AWNN selects within RIJ are still relatively close to the target row, and it bounds the average distance within that set.
Okay. And then theorem 2 wraps it all up for the missing data case.
Yes, theorem 2 gives the general MSE bound for AWN with missing data. It still has the bias and variance decomposition, and it basically generalizes the denoising result, theorem 1.
And to make things a bit simpler for analysis, they use the MCR assumption.
Right, missing completely, at random, assumption 5. Just means the missingness doesn't depend on the data values themselves. It simplifies the math.
Makes sense.
Under MSAR, plus those low-dimensional structure assumptions from before, Corollary 2 shows AWNN again achieves the optimal convergence rate for matrix completion, the same rate as the best-tuned unweighted KNN, but again, automatically, without tuning.
The theory sounds really solid. How did it actually hold up in practice? They did simulations, right?
They did. They created synthetic data using functions with varying smoothness, added noise, and poked holes in the matrices in different ways, including MCR.
And who are the contenders? What did they compare AWN against?
They compared it against a standard unweighted row nearest neighbor, row res, where they used cross-validation to pick the best K. They also used a common matrix completion baseline called universal singular value thresholding, or USVT.
Okay.
And importantly, they also included what they called oracle NN, or ON. This version was cheating slightly. It was told the true noise variance.
Ah, so comparing LN to ON shows how well the automatic noise estimation part works.
Exactly. And the results. Well, figure 1, for instance, showed LN and ON performed almost identically.
Meaning the noise estimation is pretty darn good.
Seems so. LN also consistently beat the cross-validated row, which gives some nice empirical backing to that lemma 1 theoretical result.
And USVT?
USVT did okay under MRF, but interestingly, it wasn't great in the pure denoising case, no missing data, and its performance didn't improve much as the amount of missing data decreased.
What about when they varied the smoothness of the underlying data?
Figure 2 showed that, as expected, AWN's performance improved as the underlying function got smoother. The empirical convergence rates often looked even better than the theoretical bounds predicted.
That's encouraging.
Yeah, and the benefit of smoothness was clearer when the signal-to-noise ratio was higher. Overall, the simulations really seemed to support the theory.
Okay, so summing it all up, what are the big takeaways for AWN?
I'd say the key things are, it automatically selects neighbors and their weights. No need for manual tuning like picking K. It has strong theoretical backing, guaranteeing good performance relative to other methods, even without assuming the data is strictly low rank. And it handles missing data robustly, adapting its weighting scheme column by column. The simulations back this up.
So it's a more principled, data-driven, and automated approach to using nearest neighbors for matrix completion.
That's the gist of it, yeah. A solid step forward for dealing with incomplete data using neighbor-based ideas.
Great. And for listeners who really want to get into the weeds with the proofs and the math, the paper itself on Archive is the place to go. We'll definitely link that. And also the link to the Neural Intel webpage for keeping up with the latest AI and ML research.
Definitely worth checking out the paper if you're deep into this area.
All right, so here's a final thought to leave you with. AWN shows how effective adaptive weighting can be for matrix completion. Where else in machine learning might similar ideas be powerful? Think about problems with noisy labels, or maybe transfer learning where source data reliability varies. Could adaptive weighting be a key there too? Something to ponder.
Good question.
Thanks for tuning in to this deep dive. We'll catch you next time on Neural Intel.